Okay, so today's topic is going to be bond energies and how to use bond energies to do thermodynamic calculations, as you'll usually need to do in organic chemistry. So more specifically, the goals are be able to be familiar with using these bond energies, and in particular, the big difference between doing these calculations in general chemistry and organic chemistry is you're worrying about these new ideas such as resonance energy and strain energy, typically associated with being in a ring. And the trickiest part of these calculations is correctly identifying whether a term is going to be positive or negative in a bond energy calculation. Alright, so let's get a little bit of context. So what really is a bond energy? Okay, so hopefully from general chemistry you remember this sort of diagram here. We have this Leonard-Jones potential. So if you look up here, you have two 1s atomic orbitals, such as hydrogen, and they come closer together, and due to the electrostatics, they attract each other and they form this bond here in 3. And if they're too close together, then you start getting this repulsive energy, and that's unfavorable, and that's why you see this go up here. So really what you should be getting from this graph is that when you are in the chemical bond, you are at the bottom of this energy well. Let me put that here. So chemical bond is an energy well, and really what you're looking at here is the distance of these two species from each other, and this is the energy. So when you're in the chemical bond, you're at that perfect distance where you get that bonding. It's a balance between attraction and repulsion, and when you're in the bond, you're at the bottom. So if you remember from, say, general physics, say we have a ball at the bottom of this energy well. What would happen if we were to put in enough energy to get this ball out of this well? What that symbolizes is you're going from this to this. So you're taking that bond and you're breaking that bond. So what I'm really saying here is if you put in energy, you are breaking the bond. And as you see, the energy on this axis here is going up. So bond breaking is inherently an endothermic kind of property. You need to put energy in to get this out of the well, and that breaks the bond. Similarly, if you look at the opposite, where we're going from the top here down into the energy well, you're decreasing energy, and if bond breaking is this process upward, then bond formation must be the opposite process, which is going downward. So you need to remember this well, and remember what you're doing here, because this tells you the sign convention when you're thinking about energies. So one more time, you need to put energy in to break a chemical bond, to escape from this energy well. And since bond formation is the opposite of bond breaking, when you're going downward, energy is being released in the form of heat when you form this bond. When you bring these two nuclei closer together and they form the bond, you get heat being released. So we call bond formation exothermic, and that's going to be negative. So bond breaking, positive endothermic, bond formation, negative exothermic. Okay, so why do we care about this in particular? Well, okay, let me scroll back up for a sec. So what we say when the well is deeper is that the compound that you're looking at is more stable. In other words, you want to be in the minimum state of energy. You want to be at the bottom of this well. Why does being low in energy, being at the bottom of this well, mean that your compound is more stable? Well, if you remember here, where bond breaking requires you to move this ball out of the bottom of the well up to the top, then we're really talking about how much energy we need to put in to break a bond. If you need more energy to break a bond, we consider that compound less reactive, because you need to put more energy in to get it to do anything. So the deeper this well, the more stable the compound, because the bond is stronger. You need much more energy to break the bond. Okay, so hopefully you remember this equation from general chemistry. This is the classic enthalpy of reaction equation. So the change in enthalpy you get from a reaction is going to be all the bonds broken in the reaction and all the bonds formed in the reaction. Remember, an enthalpy is really just a general gauge of internal energy. You could just think of it as internal energy in the context of organic chemistry. So it's going to be bonds broken minus bonds formed. Again, bonds broken is positive because you need to put energy in to get this out of the well, and bonds formed is negative because it's the opposite process. Okay, usually people get that sign convention pretty correct, but let's talk about the major difference between general chemistry and organic chemistry. So here's an example of a reaction, and say we want to calculate the enthalpy of this reaction. So we have this reactant over here, and it goes to this product. So you'll notice several things. The double bonds here are lost in the product, and this is in a ring, and this is no longer in a ring. So there's two different kinds of energies we see here that we can't capture in this equation. One of them is a resonance energy. So if you have double bonds arranged like this, this is called conjugated double bonds, and there's resonance energy associated with that. I'm not going to go too in depth with that right now because we'll talk about that more later on when we discuss conjugation. But just know that there is resonance energy within this reactant. The second thing is if your molecule is in a ring, in particular small rings and large rings. 6-membered rings are particularly stable, but 5-membered rings, 4-membered rings, you could get something called strain energy. So strain destabilizes a molecule because these, I guess, bonds are being forced to be angles that they don't want to be. And going from this closed chain molecule to this open chain molecule, there is a difference in strain energy that we need to account for. So remember, this enthalpy is really the amount of energy we need to use to transform this to this using this. And another way of thinking about it, and the easier way to think about it, is it's the amount of energy we need to pay to exchange this for this. So it's like you're buying this molecule by exchanging it for this molecule. And the reason we care is that there's a systems of transfers we need to do as far as bond breaking and bond formation, and each of those has their own energy associated with them. Okay, so let's talk a little bit more about resonance and strain. So you probably know from the lecture that resonance in general stabilizes a compound. Resonance we look at as good. So what that does, it means is that the overall energy of the molecule is going to go down. It's going to get more stable. What do we mean by more stable? Well, you need to put more energy in to break a bond. So what we expect is that the energy well will get deeper when we're talking about resonance. Okay, well, remember, if our energy well is deeper, we need to put more energy in to move this ball up and escape out of this energy well. So the idea is that when you're going from resonance to no resonance, you need to put in more energy to escape from the energy well. Similarly, if we look at strain, we see the opposite kind of thing going. Remember, the deeper the energy well, the more stable our compound. Well, strain isn't so great for a molecule. It means the bond angles aren't what they would like to be, so you see a higher energy state. So this well is now more shallow. That means in the context of our enthalpy is that to get this ball out of the bottom of this new well, you need to pay less than you would have paid before. In other words, it's easier to escape from this energy well than it is to escape from this energy well. And remember, when we mean escape from an energy well, we're really talking about breaking a bond. So it's easier to break a bond when there's strain than when there is no strain. Similarly, it is more difficult to break a bond when there's resonance than when there's no resonance. Okay, so what does this mean in the context of our bond enthalpy calculations? Well, based upon the ideas we just discussed, we could add these two terms over here. We're adding resonance and we're subtracting strain. Now this might be a little strange. Let's just go back to say why we did this. So resonance is positive because remember, we're looking at the perspective of how much we need to pay to break a bond. So if the resonance stabilizes the bond, then we need to put in more energy. So you need to pay more energy. If the strain does the opposite, the strain makes our energy well shallower, it's easier to break the bond, so it is going to be the opposite effect, which is negative. Again, this is when we're going from a structure, as we're looking at in this equation, when we have resonance and we're losing it, and we have strain and we're losing it. Why is it important to remember that? Well, that's usually where people get confused, and we see this kind of question every year, where people don't know if the resonance is positive or negative, and if the strain is positive or negative. So consider the same reaction except in reverse, where we're going from the open chain form back to the closed chain form. So we're going from no resonance to resonance and no strain to strain. Okay, well, first of all, we should try to figure out exactly what happened with our bond enthalpy equation, ignoring the resonance and the strain. So remember, when we were looking at this original reaction up here, when we're looking at the bonds broken, we need to break each of these hydrogen-hydrogen bonds to get the reaction to proceed. See, well, we see HH bonds over here, and we don't see HH bonds over here, which means these bonds must have been broken. On the other hand, when we're doing the reverse reaction, you see HH, and HH. These bonds were formed. So what I'm saying is that when you're talking about the reverse reaction, the bonds that you broke before are now being formed, and the bonds you formed before are now being broke. So really, you're going to be flipping the sign of this enthalpy over here, and that makes sense. If you pay 90 kilojoules per mole to get this to go forward, then if you're going to do the reaction in reverse, you'd expect the opposite thing. You'd expect negative 90 kilojoules per mole. Well, the same thing happens with the strain. So again, before we broke the HH bonds, now we form the HH bonds. And similarly, when we're talking about our resonance and our strain, from the new perspective, we're going in the reverse direction. So we're not paying to get out of this energy well, we're starting here and we're going in. So the resonance made our well deeper, so we went lower in energy, more negative, and the strain made our well shallower, so we went up in energy if we're coming down from the top of the well. So in this sign convention, when we're looking at the reverse, the resonance is going to be negative and the strain is going to be positive. So notice what I'm saying here. The sign convention depends on what sort of reaction you're looking at. So here we're going from no resonance to resonance and no strain to strain, and our resonance and strain flipped signs. Similarly, our bonds broken and our bonds formed switch places, so the overall reaction's magnitude flips. Again, we went from 90 to negative 90. Here we're going from, well, positive resonance and negative strain to negative resonance and positive strain. At this point, you might be getting a little confused, and that's why I'm telling you people confuse this every single year. There's other scenarios too. What if your reactants don't have resonance, and then you get resonance, but your reactants have strain, and they're going to a product with no strain? Similarly, look at the other possibility here, where you're going from resonance to no resonance, and then no strain to strain. As an exercise to do on your own, figure out how the positive and negative sign in this bond enthalpy equation would change under these two scenarios. And I think the point here is, when you're trying to figure out whether or not the resonance is going to be positive or negative, you should choose one of these scenarios and understand it, and then when you need to, just flip the signs. In other words, I would say choose this equation, the first one we went over, because this is the most intuitive argument. You could understand why, if your energy well gets deeper, you need to pay more to get out, and if your energy well gets shallower, you need to pay less. So I would say understand this equation, where you're going from resonance to no resonance and strain to no strain. And then if your reaction changes, you'll know whether to flip the sign here or flip the sign here. Okay, so all of this is much easier to understand when we actually work through an example. So that's what we're going to do now. So the first one I'll show you how to do. So we're told that the strain energy of cyclobutane is this, and we're given a chart with our bond energies. And this is our reaction. Okay, so the first thing you should do is what you should be familiar with from general chemistry, and that's identify which bonds are broken and which bonds are formed. It might be a little difficult if you're not used to this line wedge convention in organic chemistry, but you should get used to it rather soon. So the first thing to notice is that one of these bonds is broken. So we go from a closed chain molecule, or a cyclic molecule, to one that's open chain. So this bond is broken, so we say that a carbon-carbon bond was broke. Okay, well, we also don't see an HCl bond in our product, so we know that this HCl bond was broke. Okay, then what was formed? Well, remember, we didn't previously have a carbon-Cl bond, so we know that the carbon-Cl bond must have been formed. And similarly, we know that this H must have gone somewhere, and we know over here we had CH2, 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 and here we have a CH3. So a carbon-hydrogen bond must have been formed. Okay, all of this should be reviewed for you if you've taken general chemistry. The major difference here is that we're going from this closed molecule to this open molecule. So we're going from a strained molecule to an unstrained molecule. So if you remember from up here, going from strain to no strain means that this is going to be negative. Okay? So we've figured out what our bond enthalpy equation should look like at this point, at the negative strain. And we have no resonance here, so we're not going to include that term. The only thing you need to do is you need to write in all the bonds that were formed and all the bonds that were broke, go up to the table and substitute in these values here and do the arithmetic. And you'll get your final answer. Don't forget the units here. Okay, so now that I've showed you how to do one, you should try one of these problems on your own. So let me give you one. Okay. So at this point, pause the video and attempt this problem by yourself. Okay, I'm going to assume that you attempted the problem, and now I'm going to show you how to do it. Okay, so the first thing you might want to do is you might want to actually write out what this equation looks like in terms of structures. Okay, so we're going from cyclobutane, so that's this, with Cl2, and we're forming dichlorobutane. At this point, identify the bonds that are broken and the bonds that are formed. So we don't see the Cl-Cl bond in the product, so we know that the Cl-Cl bond must have been broken. And we see very clearly that this ring was opened, so this carbon-carbon bond must have been broken. And over here, we see two new carbon-Cl bonds that didn't exist before. So we throw those over here. Now once again, what's going on with the strain and the resonance? Well, first of all, we don't see any resonance, we don't see any conjugated double bonds. So the only thing we have to worry about is strain. And again, we're going from a strained closed chain molecule to an unstrained open chain molecule. So we're going from strain to no strain. So based on, once again, this equation over here, our strain will be negative. Okay, so we're once again going to be using the exact same bond enthalpy equation, and that's going to look like this. And once again, all you need to do is substitute in the values from the chart and solve for your strain energy. Okay, let's try one more problem, just to make sure you know exactly how to attempt this if you see it on your exam, and you probably will because it's been on pretty much every single exam since the beginning of time in Rutgers 307. Okay, so once again, attempt the problem yourself, and in 10 seconds, I'll tell you how it's done. So pause the video. Okay, once again, the first thing I recommend you do is you write out the equation in a form that you could easily see what's going on. So here, this looks like this looks like this, and this looks like this. You'll notice that we don't have any strain here because we don't have any closed form molecules. We don't have any rings. But we do see two double bonds that are conjugated. So we have a resonance going on here. Okay, so the first thing we should see is what we broke and what we formed. Well, there's a double bond here and there's no longer a double bond here. So what we're saying is that we broke a pi bond. If you remember from the hybridization video, a double bond is a sigma and a pi bond, and a single bond is just a sigma bond. So we're really going from sigma and pi to sigma. So the only difference here is that we broke a pi bond. The other thing we broke is this HH, since we no longer see it on the right-hand side of the equation. So let's put this here. As far as what was formed, we have a CH2 over here and a CH3 over here, and we also have one CH bond here and two CH bonds here. That's something you'll be able to pick up on once you've gotten used to the line wedge formula of drawing things. If that confused you, I recommend you draw all the invisible hydrogens, and you'll see it. So again, we're going from resonance to no resonance. So the resonance will be a positive contribution. Again, I feel like I'm beating a dead horse. That goes back to this equation where the resonance made the well deeper, so you need to pay more in to overcome that when you're breaking bonds. Okay, at this point, all you need to do is write out your bond enthalpy equation and substitute each of these in. Now the only part that might be a little tricky is identifying what pi bond really means. Well, it means it's the difference between the carbon-carbon double bond and the carbon-carbon single bond, which is given in this chart. So all you need to do is calculations, and you'll find your final answer, the enthalpy of the reaction being negative 90 kilojoules per mole. All right, hopefully that cleared things up for you. I tried not to overcomplicate it. What take-home message is really understand this equation here, understand the argument why bond breakage is positive, bond formation is negative, and why, if we're going from resonance to no resonance and strain to no strain, we take this sign convention here. If you understand this, you should be able to get any bond enthalpy question correct on the exam. So good luck.